Welcome, everyone, to today's session. We are here to explore the Golden Path, a comprehensive strategy for architecting massive Kubernetes deployments. This presentation serves as a construction manual for the modern platform framework, specifically highlighting our updated architecture, version 2.0. As you can see in the diagram, our architectural vision is built on three foundational concentric layers. At the very center, highlighted in pale coral, we have the core services and data layer. This is the heart of the system, where your essential applications and data repositories live. Surrounding this core is the lavender layer, which represents service mesh and orchestration. This critical layer handles the complex communication, traffic management, and coordination required to keep a large-scale system running smoothly. Finally, we have the outermost ring in serene blue, representing our security boundary and compliance. This layer acts as a vital protective perimeter, ensuring that every component within the architecture adheres to strict security protocols and regulatory standards. Together, these layers define a scalable, secure, and efficient path forward for modern infrastructure.
The paradigm shift we are observing moves us away from a focus on simple surface area and toward an understanding of multidimensional behavior. In what we call the old way, security and architecture were often viewed through a binary lens, simply dividing the world into public and internal zones. However, this model has proven inadequate for modern scale. The problem with historical binary categorization is that it ignores runtime characteristics and the potential blast radius of an incident. To address this, the new way introduces a more granular, three-dimensional approach. We now categorize systems across three key axes: workload archetypes, network zones, and runtime stacks. By looking at the intersection of these dimensions, we achieve a more sophisticated categorization based on actual behavior, exposure, and state. This transition allows for much more precise control and visibility, moving beyond simple perimeters to a comprehensive understanding of how our systems actually operate at scale.
Standardization is the fundamental prerequisite for achieving true scale. When every application is treated as a unique, custom deployment, the complexity of managing security, scaling, and debugging becomes insurmountable as an organization grows. To address this, we utilize the Golden Path, a pre-negotiated contract for deployment. By force-ranking workloads into these defined patterns, we inherently integrate reliability, security, and observability into the core of every rollout, ensuring consistency across the entire infrastructure. Phase 1 involves architecting the ecosystem through the establishment of distinct network zones. As we move into the first implementation step, we divide the cluster into tiered security zones to achieve a critical balance between accessibility and rigorous control. The architecture follows a concentric model, where traffic is required to flow inward through strictly defined gates. The outermost ring is the public or edge zone, which serves as the entry point for all external communications and handles API management. Progressing inward, we reach the DMZ or ingestion zone. This acts as a secure buffer, housing event hubs and consoles to filter and manage data before it moves further into the system. Finally, the center of the diagram represents the private or core zone. This area is designed for zero direct external access, containing our internal APIs and workers. This tiered approach ensures that sensitive core components are shielded behind multiple layers of security and managed entry points. Let's examine the specific roles of the edge and the DMZ within our architectural zones. Starting with the edge, or the public zone, this serves as the primary entry point for all internet-facing traffic. Our tooling at this layer includes API management, transitioning into an Istio ingress controller. The primary focus for the edge is robust security and traffic governance, specifically through rate limiting, DDoS protection, and surface management to ensure internal systems remain protected. Moving inward, we have the DMZ, also referred to as the ingestion zone. This zone acts as a secure buffer for administrative consoles and high-volume event processing. We utilize technologies like event hubs and Kafka here to manage data at scale. The strategic goal is to ingest and process data streams within this controlled environment before they are permitted to reach the core of our infrastructure. This separation provides an essential layer of reliability and ensures core services are shielded from direct external pressure. The private core is defined as the most secure area within our environment, containing our internal APIs, worker services, and primary databases. To manage scaling, we employ Kubernetes-based event-driven autoscaling, or KEDA, ensuring that our infrastructure adapts to workload demands efficiently. Regarding connectivity, a strict traffic rule is in place. Zero direct external access is allowed. All traffic must arrive via ingress or event hubs, maintaining the integrity and isolation of this critical zone. To summarize the first phase of our network architecture implementation, we must first ensure several critical prerequisites are met. This includes having a Kubernetes cluster fully provisioned, Istio installed to manage ingress and service mesh traffic, and established namespaces for Event Hubs or Kafka. Our primary goal for this phase is to establish a clearly defined network perimeter with segregated traffic flows. By successfully implementing these boundaries, we significantly reduce the potential blast radius in the event of a security incident. Finally, it is important to address a common pitfall: misclassifying internal admin consoles as private zone workloads. To maintain a robust security posture, these consoles should actually reside within the DMZ. This placement is essential to prevent direct exposure to the core network, ensuring that administrative tools do not inadvertently create a pathway to our most sensitive internal systems. Moving into Phase 2, we focus on establishing a clear taxonomy for our workload archetypes. This second implementation step requires us to categorize every container in the environment based on two key criteria: how it is exposed to traffic and how its lifecycle is managed. By doing this, we can standardize operational patterns across 5 primary archetypes. First, we have edge services, which act as the entry points for external traffic. Second are mesh services, which facilitate internal service-to-service communication. Third, we define event workers, designed specifically to process asynchronous event streams. Fourth, we account for batch jobs, which are short-lived tasks that run until a specific process is complete. Finally, we include stateful apps, which manage persistent data and require unique management strategies compared to their stateless counterparts. This classification is essential for building a scalable and predictable infrastructure. Category 1 focuses on edge services, which are defined as internet-facing applications such as backend for front-end services and public web apps. The network path for these services flows from the public internet through an API gateway and into the Istio ingress. Because these services are exposed to external traffic, they must meet 3 critical requirements: robust DDoS protection to maintain availability, precise rate limiting at the gateway level to manage load, and traffic routing managed via Istio for granular control. Category 2 focuses on mesh services. These are defined as internal microservices that never interact with the public internet. The network path for these services is strictly limited to service-to-service communication. To maintain a standardized and secure environment, we follow the Golden Path configuration. This starts with using cluster IP as the service type to ensure internal-only access. From a security perspective, Istio sidecars are required for all services within this category. This allows us to enforce mutual TLS in strict mode, ensuring that every connection is both encrypted and authenticated. Furthermore, we offload reliability concerns to the infrastructure. Automatic retries are handled by the mesh itself, removing that complexity from the application code and ensuring consistent behavior across the entire architectural footprint. Category 3 focuses on event workers, which are defined as asynchronous background processors. Looking at the network path, these workers have no ingress. Instead, they function by listening directly to event hubs or streams. When establishing a scaling strategy for these components, we use KEDA, or Kubernetes Event-Driven Autoscaling. The most effective metric for scaling is message lag, or queue depth, as this directly reflects the actual workload demand. It is important to remember that scaling based on CPU or memory usage is considered an anti-pattern for event workers, as these metrics often fail to provide an accurate representation of the pending work in the queue. Moving into categories 4 and 5, we explore batch jobs and stateful applications within our architecture. Category 4 focuses on batch jobs, characterized by the run once and die model. These are ideal for intermittent tasks, such as nightly cleanups or automated reporting. Technically, these are implemented as Kubernetes cron jobs using transient pods that spin up to perform a specific task and then terminate. A key security feature of this category is that these pods operate with no open ports. Category 5 addresses stateful applications, which are necessary for legacy systems or data-heavy workloads that require data persistence. Unlike stateless services, these utilize stateful sets paired with persistent volume claims, or PVCs, to maintain a consistent state across restarts. To ensure proper traffic management, we implement Istio Session Affinity, commonly known as sticky sessions. This mechanism routes specific users to the exact same pod for the duration of their session, ensuring continuity and performance for state-dependent workflows.
In Phase 2, we focus on workload taxonomy to organize and secure our services systematically. Before proceeding, it is critical that we have met two prerequisites: a full inventory of our current application portfolio and a completed dependency mapping. These foundations allow us to accurately categorize how services interact. Our goal is to achieve two primary outcomes. First, we need clear network policies that distinguish between ingress and cluster IP traffic. Second, we must implement standardized discovery mechanisms for every service to ensure seamless connectivity. One common pitfall to watch out for is unnecessarily exposing internal microservices to the edge. This creates avoidable security risks. To mitigate this, our default posture should always be mesh, unless there is a proven requirement for public access. By following this secure by default approach, we maintain a robust architectural perimeter. Transitioning to Phase 3, we address runtime optimization, often referred to as the stacks. The third step in our implementation process involves tailoring the Kubernetes resource strategy to align with specific programming language profiles. As illustrated by these three pillars, we categorize our environments into the JVM stack, the native stack, and the dynamic stack. It is a common misconception that a single deployment template can serve all application types. In reality, a Java application requires a significantly different configuration than a Node application. Profile A focuses on the JVM stack, encompassing languages and frameworks like Java, Kotlin, Scala, and Spring Boot. While these are powerful tools, they're characterized by a high memory footprint and slow cold starts. To address these challenges, we follow a set of golden path tuning practices. First, for memory management, it is crucial to configure max RAM percentage in the Docker entry point to ensure the JVM operates efficiently within container constraints. Second, for liveness and readiness, we employed generous startup probes of 60 to 90 seconds. This buffer prevents Istio timeouts while the application initializes. Lastly, regarding observability, we employ the auto-injection of Java agents to facilitate B3 header propagation, which is vital for maintaining tracing consistency across our distributed environment. Profile B highlights the native stack, encompassing languages like Go, Rust, and C++. The primary advantages here are a tiny resource footprint and near-instant boot times. However, this rapid startup presents a unique race condition risk. Because the application initializes so quickly, it may attempt network calls before the Istio proxy sidecar is fully ready, resulting in initial connection failures. To resolve this, you must set hold application until proxy starts to true. Additionally, for the base image, we recommend using distroless or scratch images to ensure the smallest possible attack surface and minimum overhead. Profile C, known as the dynamic stack, focuses on runtimes like Node.js, Python, and Ruby. These languages are primarily single-threaded and are notably sensitive to CPU performance. To optimize this profile according to the golden path tuning, we prioritize horizontal scaling over vertical resizing to better handle load across multiple instances. For availability, we mandate a minimum of 2 replicas. This prevents total downtime if one instance is occupied by a blocking operation. Lastly, tracing within the stack requires manual header propagation, such as X request ID, directly within the application code to ensure end-to-end request visibility. Moving into Phase 3, our focus shifts to the optimization and stabilization of our runtime stacks. To successfully navigate this phase, we have identified a core prerequisite: the implementation of standardized base images across all stacks, specifically leveraging distroless, Alpine, and Debian distributions to ensure consistency and security. The expected outcomes of this transition are twofold. First, we aim to eliminate cold start timeouts within the JVM environment. Second, we seek to resolve and eliminate race condition crashes within our native implementations. To ensure success, we must be vigilant against 2 common pitfalls. First, avoid using CPU metrics as a scaling trigger for the JVM stack. Memory is the actual resource constraint in this context. Second, we must remember to set minimum replicas for single-threaded dynamic applications to prevent availability issues during scaling events. Moving into the fourth step of Phase 4, we examine the Unified Compliance Stack. This model establishes a standardized security framework across 3 integrated layers to ensure consistent governance throughout the development lifecycle. At the foundation, Layer 1 focuses on data sensitivity. For Tier 1 workloads, such as those involving PII or financial data, we mandate a zero-trust posture. This includes the enforcement of strict MTLS for all internal communications and the implementation of egress deny all policies to strictly control and monitor outbound traffic. Building upon that foundation, Layer 2 addresses base images. We minimize the attack surface by enforcing the use of a trusted registry. This ensures that every application is built on top of hardened Alpine or Debian images that have been pre-vetted and optimized for security. At the top of the stack, Layer 3 focuses on build automation. To eliminate the risks associated with custom, error-prone Docker files, we utilize cloud-native build packs. These build packs use auto-detection to standardize the containerization process, ensuring that security and compliance are integrated into the build process automatically. By unifying these layers, we create a robust environment where security is a core automated component of the infrastructure. Phase 5 focuses on the intake mechanism, which serves as the critical bridge between developer intent and automated environment configuration. The process follows a streamlined workflow. It begins with developer input, moves through our centralized automation engine, and results in precise config injection into the target environment. To understand how these configurations are determined, we look at the Golden Path Logic Map. This map defines the specific infrastructure stacks applied based on the nature of the application. For instance, a Go service exposed to the public internet is automatically assigned an edge category configuration. This utilizes a native stack with distroless images for a reduced attack surface and a proxy hold for managed traffic flow. In contrast, an internal-only Java application triggers a mesh category configuration. This applies a JVM-optimized stack featuring cluster IP for internal service discovery and a 90-second startup probe to account for the JVM's initialization period. Finally, for asynchronous Python workloads, the system selects the worker category on a dynamic stack. This automatically integrates Kata for event-driven autoscaling and ensures a minimum of 2 replicas for baseline availability. By codifying these paths, we ensure that every deployment adheres to organizational best practices without requiring manual intervention from the developer. This implementation checklist serves as our final validation for production readiness. We begin by categorizing the service intake as edge, mesh, or worker, which dictates our discovery strategy. Selecting the right runtime, JVM, native, or dynamic, is equally critical, as it directly influences our resource limits and probe configurations. To maintain system resilience, we ensure that all asynchronous tasks are decoupled and routed through event hubs, using Kata for event-driven scaling. For comprehensive observability, we must confirm that tracing headers like XRequestID and B3 are propagating across all services. Lastly, we enforce a strict security baseline, requiring hardened base images, mandatory MTLS, and granular egress rules to protect our architectural integrity.